인사할 시간도 많습니다. 여러분의 시간을 낭비해드릴
konnichiwa, kunihongoha.
안될과학 인터뷰입니다. 반갑습니다. 네, 안녕하세요. 반갑습니다. 네, 안될과학 항성입니다. 오늘 구글에서 최근에 개발한 양자 프로세서인 윌로우 개발에 참여해 주시고 퀀텀 프로세서의 디렉터를 맡고 계신 유채님과 인터뷰를 할 예정입니다. First of all, really thank you for accepting this invitation. Could I ask to briefly introduce yourself?
Definitely. Hi everyone, my name is Yu. I'm a director working in Google Quantum Lab. Basically, my job is really trying to produce high quality quantum processors. I have been in this team for, in fact, this is my 11th year. I just passed my 10th years. Pretty fun journey. I start my initial journey actually in a completely different field, and then I end up with this field, and I have seen a lot of progress in the last 10 years.
That's very amazing. So you try to develop the very latest, very new version of the quantum processor, right?
That's right. That's what we're doing.
That's amazing. We heard that Google recently developed a very new quantum processor, right? Which is called Willow. So what's the significance behind the naming your quantum processor Willow? How does this name, along with your previous Sycamore, reflect Google's quantum computing philosophy?
Yeah, that's actually an interesting question for us to tell a little bit the story behind the scene. So as you can probably remember, in 2019, we reviewed this, what we call the older generation Sycamore. Willow means to like rebuild from that particular architecture. So we name all the processor after California plants. But Willow specifically is something you can take a piece of that, you can replant, and it will grow very strongly. The reason they can grow very strongly because it has very strong root. So the reason we pick up Willow is we really feel this is like a reborn of Sycamore with very strong root, and then we have the root is basically high performance and scalability. This is why we're so excited with this name.
Oh, that's very good. Because we interviewed Karina Chow last year when Google developed the Sycamore, but you say that it is old version that's very amazing because this time it's in this field the things are changing very fast. It seems like it. Could you explain 10 to 25 years versus 5 minutes quantum advantage in terms of our viewers can understand? Perhaps with a real world analogy.
Yeah, definitely. So first of all, let's spend just like a minute to define what is quantum advantage even means. So in our community, quantum advantage really means you are doing something in quantum computer that cannot be done with classical computer. That's why we say that's an advantage to use quantum computer. So in this specific case, what we have been doing is we're running an algorithm called random circuit sampling. So it's something you just run certain thing and you look at the outcome with a quantum computer. It's definitely quite amazing how well quantum computer can do this because as the number you quote, it's a 5 minutes versus like 10 to 25 years. It's just this is the number just beyond even the age of the universe. This is
right.
Crazy to imagine. So you asked me, hey, how can I understand what you guys have done? So just put it in this way. So imagine we have 100 qubit. Each qubit you can consider in a simple language a dice. I mean, this is something we can imagine in the real world. It's a dice. But what's the difference is quantum computer or quantum bit, it's dice, you only have few choices. But quantum computer, you have much more variety of choices. However, what's this magic in this particular test is, okay, now I give you 100 dices. Quantum computer is someone like has a magic hand. Not only you can rotate one dice at a time, no, you can do all the rotation on different dice at the same time, and they collide into each other, they bounce against each other. At the end of the day, you have no way to tell what is outcome you can predict. A quantum computer can actually predict that very, very good. So this is one way for you to understand how this whole thing works.
That's very amazing because like even the very hard problem or very hard computational, it takes like 10 to 25 years to calculate something in the classical computer. But with the Willow quantum processor computer, can calculate in 5 minutes. That's what you said, right?
Yeah.
That's very amazing. What's the biggest challenge in developing Willow, and how did your team overcome it?
Yeah, this is actually a pretty long history how this whole thing developed. If you remember, we discussed earlier, Willow was a new reborn from Sycamore. So the major change or major improvement compared with Sycamore is actually on the performance or the qubit. However, those quantum bits are extremely sensitive to external environment. They're very easy to have errors. So the whole community, to do this thing, is really trying to figure out how can I build something such as the qubit lifetime can become longer and longer. This, in fact, is the major thing we have been focused on to upgrade from Sycamore to Willow. So you ask me, hey, what induced that major change? It's a basic combination. The device we have, we call quantum processor. We need to basically continue to improve the exact design and how we put things together. That's actually an extremely careful job. You need to figure out how to do. And meanwhile, not only you figure out how to improve the design, but also you need to build it, you need to fabricate it. That process is also very dedicated, and you need to have very special tool, extremely well-trained engineer, really do that extremely carefully. But those are the lessons we have learned step by step in the last couple of years. In fact, this is actually a lot of things we're learning in collaboration with academic group as well.
Okay, so Sycamore was very, very latest to new computer. It was very revolutionary, even Sycamore was. And the Willow, even better, right, than Sycamore. Yes. So can you tell the difference between the Sycamore and the Willow? What's the improvement between from the Sycamore to the Willow? In qualitatively or quantitatively in any aspect.
Yeah. So one metric we can use is a lifetime of qubit. In other words, if you store some information in a quantum bit, how long it will last before eventually those information will get just diffused, go away into the environment. The biggest improvement we have done compared to Sycamore with Willow is this lifetime. We improve them by a factor of 5, so 5x.
5 times.
5 times, yes.
Wow.
So that really have a big impact across many things. Once that is much longer, then you can really have a better time to improve, for example, what we call quantum gate, how you rotate the qubit. Everything's better with longer lifetime.
What about the number of the qubits?
Yeah, number of qubits also get improved. So in 2019, when we did the first, what we call beyond classical demonstration, that is around 54 qubit. And then the experiment was done with 53 qubit. In the most recent experiment we have done, was actually done with 105 qubit devices. Actually, you asked a very important question. When we talk about those performance, everything, it's very important to understand you need to really code those numbers in a system. Because if I only need to build 1 qubit, we know how to build this extremely well. But when you need to build a system with 100 qubit, they're very different tasks.
Oh, okay. I have a quick question. Is the reason that the lifetime of the qubit got increased because of the number of the qubit get increased from the Sycamore to the Willow?
If I stay at the same number of qubit, it's actually easier for us to improve the number even further. So at the same time, we improve this lifetime, and at the same time, we improve the qubit number. This is kind of double challenge we need to overcome. And this actually, as I mentioned to you, is a combination. We need to improve the design, improve the fabrication, as also a lot of setup, how we set up the filter, the measurement system, everything is kind of upgrading across the board.
Oh, that's very much some improvement. That's very good. And you lead all this process, right?
Yeah. So I work with this team called Quantum Processor Team. Our job is really trying to figure out how to build the best possible processor.
That's very amazing job. Okay, so next question is, Willow shows the reduced error rate as you add more qubits, which seems actually counterintuitive. Could you explain the breakthrough in simple terms?
Yeah, I actually agree with you. This is quite counterintuitive.
Yeah.
In what sense? Typically, if you think I want to do something, if I need to deal with 1 qubit, it's easier. But if I deal with 5 qubit, okay, if they have error, the probability you have error is higher. But the magic here is so-called quantum error correction.
Quantum error correction.
Quantum error correction is the keyword. What that means is actually we use several qubits together, not to do, say, algorithm. It's just put them together, we form the so-called logic qubit. Okay. Effectively, let's be specific. Let's take 5 qubit, we put them together, say, 5 of you guys are 1 single qubit. If I have 5 qubit, the rule, in a simple language, the rule of quantum action is if 1 guy has an error, I don't really care. Only time I said something has an error, this whole logic qubit has error, is at least larger than 50% of qubit. In this case, I need 3 qubit to have error at the same time.
Oh.
So you can imagine the probability for 3 qubits have error at the same time can get reduced by probabilistic calculation. And then now I can go even further. Instead of have 5 qubits, I can give you 9 qubits. I can give you 11 qubits, everything. So now in the case of, for example, 11 qubits, instead of just 3 qubits have error at the same time, I need 6 qubits. It's even harder. So I can keep going. And then things become, in terms of probability, become less and less to have error. Of course, this is extremely simple language. The actual quantum error correction is much more complicated.
All right. So you mentioned about the error correction techniques. So I have a quick question about that one. So you've adapted error correction technique from technology like 5G services or SSD services or something like that, right? So what inspired this innovation to approach to apply this quantum processor?
Yeah, that is definitely right. So error correction is actually pretty common technology, not only for quantum computing. In fact, it has existed for, I would say, conventional electronics for many years. Like the example you mentioned, information communication as well information storage, 5G or SSD. There, the basic principle is just I generate multiple copies. When something goes wrong, I have a backup. This is simple. Similar idea, but slightly different, happened in in the quantum computing language. In quantum language, what's different is you cannot have backup because information, in other words, if I have information 1 qubit, you cannot copy exactly to the other one. This is quantum mechanically not allowed. So what we can do is actually adapt that idea. As I mentioned to you earlier, okay, instead of using one, I use multiple. So what we're trying to do is those smart quantum error correction scientists create this what we call quantum error correction. So the key there is not only have backup, it's okay, I take I take 1 qubit and I expand the many and I use that as one single logic qubit. The subtlety between quantum error correction versus classical one is, okay, quantum error correction, you need to keep trying to detect whether or not you have error. But this kind of probing of detection, you need to be extremely gentle. In other words, you want to detect that information enough, but you don't disturb how quantum bit is operating, is working. If you can do that, you know where the error coming from, and you can do correction based on certain algorithm to correct that, then quantum computer can actually run very smoothly.
Oh, okay, I see. Oh, that's very good. Oh, that's very how can I say, it's mind-changing things like right. Next question is, why did Google choose a superconductor qubit for Willow? What advantage and challenges come with these choices?
Definitely, there's many choices to build a quantum computer. In other words, you need to decide which unit you want to use to represent quantum bit qubit. A more intuitive choice could be something like an atom. An atom itself, it's so small, and most of the time it behaves quantum mechanically. You can use a quantum bit. And there's other platform as well. So in our particular lab, our choice is using, as you said, superconducting qubit. The way to look at that is simple. There's a keyword, superconductor. And so we use superconductor to build a circuit. This circuit contains 2 fundamental elements. There's a capacitor, there's an inductor. Those are the terms you probably know about already, for example, back in high school or in college. Those are pretty conventional terms that you can literally see in your phone, any conventional electronics, capacitor, inductor. What's differently goes into a few aspects. Number one, as we mentioned earlier, we are using superconductor. For good reason, because superconductor has no resistance below certain temperature. So that reduces the dissipation, that helps you to protect the lifetime of the qubit. And then what also special is this particular inductor, we're not using the standard inductor, we're using something called Josephson junction. It's a one special structure derived from superconductor. So by combining those, actually you can build, to a good extent, this is very similar to like conventional integrated circuit. You have L, you have C, capacitor, inductor, you just patch them together. So then once you understand that, I feel the advantage and disadvantage become easier to understand. The advantage is you heard a very similar concept, capacitor, inductor, just as conventional electronics. So we can borrow a lot of technology, no matter fabrication and design, from conventional electronics to this line. So we know actually how to build this to a good extent to start with. It's a very good way to borrow the knowledge. On the other hand, we kind of have to use superconductors with the reason I mentioned to you earlier. But superconductor will not become superconducting until you go below certain temperature. So we kind of have to operate our quantum computer at a very low temperature. It's not impossible. It's definitely possible, quite manageable, but it generates some overhead for you to. You need something special. Additionally, as I mentioned to you, a more intuitive example for quantum bit is atom. Atom is good in the sense that it exists in nature, but it's extremely hard to control. It's so tiny, you cannot really feel and see it. The way we are building this is what we call actually artificial atom.
Artificial atom.
It still behaves like an atom, so it follows quantum mechanics, but it's artificial in the sense that this is much bigger. So you can touch it, you can control it. This is the way how you actually really can use it as a.
How much bigger than a real atom?
It's actually much bigger. You can literally see a quantum bit
really?
with your eye.
Oh.
Yeah, we're really talking about millimeter scale. So this comes with definite advantage and prices. The reason we make them big is, number one, it's easier to do fabrication. We can use conventional fabrication method. Number two, we purposely make it big such that it's easier for them to talk to each other and talk to, for example, your control system. But the price you pay is because so big, you can imagine, not only they talk to the thing you want them to talk to, they talk to the thing that you don't want them to talk to, and then the lifetime can suffer. Typically, compared with an atom or other smaller system, the lifetime of superconducting qubit is shorter. But in the last couple of years, I would say we improve a lot in this axis.
I'm surprised that even the artificial atom is really that big and still follow the quantum mechanics.
This is absolutely one of the most miracle things you have
really?
to see, in your eye. I mean, to some extent, it's not that difficult to understand because the big discovery of superconductor is this. Superconductor is one of the few examples in nature. The coherence, the phase coherence, spread across macroscopic size. It's not tiny. No, we're really talking about very large scale. That's why we want to use superconductor, because this coherence can maintain over distances.
If there is a resistance, they lose the information or the quantum mechanics not working on the without the superconductor.
Yes, I mean, there's many ways you can perturbate the system such that they stop working. For example, we introduce a lot of control into the system. You pay a price for this control. Not only they deliver signal to control system, they also introduce perturbations such as the system will just stop and then they lose information and then the qubit just will stop working.
Okay.
And then in fact, it's kind of amazing how quantum bit or this particular thing are sensitive to external environment. So there are certain things we discovered recently with our qubit interact with cosmic ray. It's just hard to imagine cosmic ray. They happen to you all the time, shine to your hair, you never notice. But qubit, they notice that. They're extremely sensitive to any small perturbation around them.
All right, that's right. Okay, that's good. So my major is actually astronomy and astrophysics. And I am very interested in that there's been discussion about the quantum computing in space, including the Starship quantum cluster. That's what I heard. That concept was amazing. What possibility do you see here?
Yes, I agree with you. I think that concept is quite amazing and it's quite interesting to think about. But I would say, in reality, even though technically, I will say this is not impossible, but I will consider this is pretty difficult. Okay, what's useful for outer space? Okay, number one is already cold. You probably don't need any special thing. You can pull down a superconductor. Number two, I mean, vacuum level is much higher in outer space, so you kind of have either way. You have less perturbation from environment, so it's a cleaner environment. On the other hand, I would say building a quantum computer is pretty tricky. It's not just build the processor or chip. You need to build a large control system, everything. It's just a little bit hard for me to imagine. At least it's easy to build this in outer space, given they are so distant away. To me, as experimentalist, I feel probably the first thing to do, or the most important thing to do, is can we just build the first one first on Earth?
Or on Earth.
We can do that. Let's figure out what to do next.
That's good. So let's talk about what we can do on Earth first then. Can you walk us through the concrete example of how Willow might accelerate the new drug discovery or something like that? How can we use the Willow for that field?
Yeah, so Willow, or in general quantum computer, are known to be doing certain things that are very good. What you mentioned is one of them, but I would say this belongs to a big category called quantum simulation. What that means is you use quantum computer to simulate some very complex system, and those systems follow quantum mechanics. In fact, this is a vision provided by Feynman almost 60 years ago, and this is one of the most outstanding example. So let's imagine what is a drug. The drug is composed by certain fundamental molecules,
Right.
electrons, atom. The most tricky part to understand how to design a drug is, hey, can you fully understand, predict what is the property if you combine certain molecules together?
Right.
Are they intact? Whether or not they will show certain aspect or property. This is something extremely difficult for classical computer to predict because it completely follow quantum mechanics. And then once you go the system to be larger and larger, this complexity just grow exponentially. At some point, this become impossible basically for classical computer to do. On the other hand, quantum computer fit very naturally to do such a job. In other words, I can choose quantum bit to mimic this guy mimic electron, that guy mimic atom, a certain distance, they interact in a certain way. By doing those, basically we can predict very precisely how they different part of the molecule interact with each other, how they form the actual drug. And then from that, I think you can actually derive how the property can look like for this particular drug.
That's very good. Like an AlphaFold or something like that, they are using even AI, but they're still using the classical computer. But we're saying that those are very good to try to figure out the structure of the protein or something like that. First of all, we have to understand how the structure of the protein first. Then we can develop the new drug. But even using the quantum computer by the Willow or some other advanced processor thing in the future, it will be much more faster and it will much more accurate. That's what you said, right?
Absolutely, yes.
Right. Okay. So in terms of, we just talked about the AI. Everyone using the AI in everyday life, our daily life, right?
Yeah.
So how might the combination of the quantum computing and AI transform our daily lives in the future?
That's definitely a very good question. It's actually an interesting question. I also keep thinking day to day as well. The first thing I want to point out, first of all, with the combination of AI and quantum, sometimes the combination really works in text which they interact with each other, really help each other, but in many areas, they perform very differently. So I can give you a full example of why they can support each other. Let's go back to the example we just talked about, like drug design and discovery. The way to look at those is they perform differently. The supercomputer is really considered as an extremely powerful computer that can do things extremely fast. In simple language, this is like a supercar. You can drive it extremely fast. But what can AI do? AI is not a supercar, but AI is an extremely smart driver.
Oh, okay. That's a very good aspect.
Now you can imagine, right? You have a supercar, extremely fast, smart driver.
Oh,
Put
okay.
them together. They can take you to the right destination in the fastest way.
Uh-huh.
Go back to the drug design. What that means is quantum computers are very good in terms of computing, as we discussed, exact interaction, how molecules structure with each other, such that we can predict the property. However, what AI can do is, hey, if I know certain property of this particular design drug, how that attached to certain functionality, how this perform, heal certain diseases. This is actually what AI to do, trying to draw correlation between certain thing to certain other thing. So combining those, I feel this fulfills the entire process of drug design. I can give many other examples of how this works as well, but I would like to turn things around because right now we talk about how, for example, quantum computer can help AI. But what you probably didn't know is sometimes AI can also help quantum computer. What that means is we have a quantum computer. However, it's not obvious how you best use it. Sometimes, especially not only you have control, you have a lot of complicated environment. You can do the best you can do, take one by one, but sometimes AI is extremely smart. So that is actually this field is really people figure out how to use optimization to do the best quantum control, and this help you to really best use quantum computer for the best performance.
Okay.
In fact, if you read our recent paper, we're using Willow, this error correction paper, we used AI, not only for control, we use AI for quantum error correction. AI is just a smart machine to tell you how to do certain correlation in a fundamental way.
Oh, that's good. Even developing the Willow itself, you use the AI as well.
Yeah.
All right. So next question is, I'll just try to ask you about in terms of the practical considerations. Many people are concerned about the quantum computers breaking current encryptions. How should we understand this challenge with the quantum computer part?
Yeah, we definitely very well understand the concern. So at least, yes, on paper, that's well-defined algorithm, how quantum computer can do such a job. But in reality, we feel this is something, I would say, practically pretty far away. Let me be clear. The current Willow, we cannot do it. I say we cannot break this particular task. Let me give you a specific number, such that you understand why I'm saying so. In order to break ISA, you need 4 million qubits.
4 million. Right now,
This-
we're talking about 105 qubits.
Exactly. Now you see the difference. Why we need 4 million qubits? Because we need to actually have that number of qubit to use error correction, to have a very functional logic qubit, then you can do it.
Okay.
It's a pretty complicated task for it to accomplish. Willow, we're talking about 100 qubit right now.
Right.
So this is pretty distant away. That's why I'm saying we're probably talking about on the order of 10 years before a capable quantum computer can be built and do such a job. What that really means is that, yes, on paper, quantum computer can break encryption. In reality, I really feel internet security, which is related to encryption, is really have a lot of years to really understand and prepare for this post-quantum encryption. In fact, as you can imagine, I mean, what do we have? Google. Google is the internet company. If the internet is not secure, we're as well. So this is kind of put us, we kind of, on one hand, we build a quantum computer. On the other hand, we really support for the entire community. We work with everybody, entire community, to see how can we prepare for this post-quantum era. So what we do is we really work with everybody, improve the technology, set up a standard. I mean, if you look at the news in 2004, the US National Institute of Standard and Technology, they just released 3 different new standards. This really helps the entire community prepare. Yes, we're progressing quantum computer, but there's additional technology we're building, such as by the time it comes, we can still enjoy a secure internet.
Oh, that's very good. Okay, thank you. And where does Willow fit in Google's quantum roadmap, and what's the ultimate goal, and what will be your next goal for after the Willow?
Let's talk about the final destination first. Where is our final destination? Our final destination, as we mentioned earlier, is really to build this full functioning with error correction quantum computer, such that we can use it to do everything we're hoping to do. All those beautiful algorithm application, practical application that is beyond classical capability. That is final destination. So our roadmap basically take that destination and we set up several steps, which we have milestones how to achieve that. What Willow, this particular experiment we have done, I would say in total we have about 6 milestones in the roadmap. Willow is somewhere between the second one and third one, closer to the third one. That also basically brings us to your other question, what is the next? It's our third milestone. The milestone, what we call is a long-lived logical qubit. Logical qubit is something we discussed earlier already, how to form with superqubit. And this is exactly what we have shown with Willow more recently. What we have shown is language we're using is logic error rate. So we have logical qubit, how often this logical qubit show up with error. Right now, we're at a 10 to minus 3. We're getting close to 10 to minus 3. The goal for us is 10 to minus 6. So we need to improve.
Minus 6?
Yes, we need to improve by 3 orders of magnitude.
Wow.
The reason we pick up that, because we think that level error rate is where you need it if you want to actually to do practical algorithm, especially on the one we have studied a lot, like quantum simulation, those kind of things.
That's going to be amazing because you're talking about order of the 3, right?
Yes.
Okay. Oh, I'll expect that, and hopefully we can interview next time when you achieve that one. Okay. So we have a few more questions that I want to ask you about it. With many companies entering quantum computing right now these days, how do you see this field evolving in quantum computing part?
Yeah, this actually is pretty, I would say this is an interesting journey I myself have gone through. As I said earlier, I joined Google 10 years ago. In fact, this is where we start this particular hardware lab in Google. And before that, I was a postdoc in the university laboratory. So what I have seen is, I would say, a little bit more than 10 years ago, this whole quantum computing research are very heavily academic driven. Most of almost everything was done in academic group. Then industry participants start to enter more and more. I think this kind of have a transition to be completely academic focused to, I would say, a collaboration between academic and industry. However, what I feel is very good about this, it's a pretty healthy ecosystem in a sense that different players really play different responsibility and roles. For example, academic group continue to be very important in terms of bring innovation and really help us to solve some open challenges. They bring a lot of expertise in terms of improving qubit design, for example, improve the lifetime of the qubit. They are really trying to help us solve some fundamental challenges, which is open and takes a long time. On the other hand, industry player, as you can imagine, with more resources, as well as, I would say, capability coming from engineering aspect, and as well as a lot of integration experience, our job is then to focus on building bigger and more integrated system. And then our job is really help to take a lot of different pieces and put them together and ensure everything's working. But overall, I feel this collaboration between academic, this interplay has been very well. We're having very good community.
That's very good. Wow. I'm very excited about to see how this industry and this quantum computing field can evolve for the next 2 decades or so. Okay, couple of questions more. And when might we see quantum computers being used in practical real-world application?
The question is, there's no unique answer. Why I'm saying so? I think when we say real-world application, it's really up to what kind of application and which group of community you're talking to. Let me give you 2 extremes. One extreme is quantum computer actually literally right now are used to study a lot of physics-oriented problem. As you can imagine, one of the big challenge in terms of physics community is really trying to understand when you have many atoms fit together, how they interact, how they work with each other. This many body physics, a lot of phenomena, physicists just really love to have some superpower to understand what's going on. This, in fact, is something we already use quantum computer to help us to solve. Number one, identify new phenomena. Number two, really do some computation that is become more and more challenging for classical computer to do. So if you focus on this particular target audience, I would say this can be quite near term from that perspective. On the other hand, those examples we talked about earlier, for example, battery design, or even the example we talked about earlier, like I say, I think a lot of more advanced algorithm, they will require full function quantum computer with very large scale to be built. Those, I would say, will take us a little bit more. And then the most important part, in fact, for us is, can we find some middle ground? Can we build something that is better than what we have now? And we can do some amount of error correction, not the full error correction, and it's not enough. That is the most active kind of area working on in terms of finding the right application in this particular area.
That's okay. Thank you. I think the quantum computer and classical computers have different roles to play. I think, even though for the future, right? So that's why we're not going to be very everyday use of the quantum computers. Still for the future, like were you going to use every day for computers will be still classical computer though, right?
Oh, I absolutely agree. I cannot agree more. This is something actually I think it's important for the wider community to understand.
All right. Yeah. Hopefully me too. That's why I'm trying to interview with people to see this interview as well.
I think you captured that very well.
Thank you. And finally, what's the biggest misconception about the quantum computers that you'd like to clarify for the people, to the public?
Yes. So actually, I want to add to what you just simply said, because this is actually the most common.
Oh, okay.
Okay, when I can use your quantum computer, say, oh, I'm not sure when, because quantum computer once being built, I would say people should consider this is not a replacement of your laptop or conventional computer. You should consider that a very special supercomputer. It's a large computation facility. When it comes down to day-to-day, play video game, you watch YouTube, use your laptop. Quantum computer should be used on very certain well-chosen application, like the one we discussed earlier. But day-to-day, no. Quantum computer is not something you can buy, put at home, and use it. Number one, quantum computer gonna be expensive. Number two, it's gonna take a lot of power. I'm not sure your house can support that.
Right now, as same as right now, you cannot use a supercomputer in your house.
Exactly,
Right?
exactly. It's used for solve some of the most difficult problems for the large community.
Okay, that's very good. Thank you for having me over the great time. We're about to wrap up now. And thank you so much for providing such a great insight about the latest quantum chip, Willow, and quantum computers. I'm very appreciated about that. Thank you.
Great pleasure.
네, 지금까지 구글의 퀀텀 프로세서 디렉터인 유첸과의 인터뷰였습니다. 여러분들도 양자 컴퓨터에 대한 이해와 이번에 구글에서 새로 개발된 윌로우에 대해서 조금 더 많은 인사이트를 얻으셨길 바랍니다. 인사할 시간도 많습니다. 여러분의 시간을 낭비해드릴
끊이지 마. 그냥 과학.
안될과학 인터뷰였습니다. 감사합니다.